M1. Hopefully everybody is being healthy and safe, practicing social distancing. Today's video is the only video that I will be creating for the week. It'll be focusing on three concepts: percent composition and how to figure that out, empirical formula and how to figure that out from either percent composition or actual experimental data, and then molecular formula from all of the above. So we have to define what those three things are: percent composition, empirical formula, and molecular formula, how they're different, how they're the same, and then also how to calculate or determine their information. So this week, homework is going to be slightly different. There's one handout. It will be in your OneNote folder. It will be labeled as percent composition, empirical formula, and molecular formula, as would say. There is a handout there for you to print out. And then when you print out that handout, I would suggest that you write directly onto that handout, do the work, and then you're going to scan if you have a scanner, or take pictures, clear pictures of your work in proper orientation for me to be able to read to see whether or not you've done it correctly. And then also you can check your answers on Google Classroom, because there is a file there, a homework assignment that allows you to input your answers to see whether or not you did it correctly. So anyway, that's this week's homework. It's one handout. Again, the challenge this week is getting the work scanned or taken pictures of with your phone or your parents' phone or whatever, and then getting it copied back into the OneNote page. So let's see what we got on our table this week. So the first thing we're going to do is look at the concept of percent composition. And percent composition is fairly simple in that it is a ratio. It is a percent, but it is the percent of the mass of each element in a compound. So for instance, carbon dioxide is CO2. So 1/3 of the elements are carbons, and 2/3 of the elements are oxygen. However, since oxygen has a greater mass than carbon, if you were to look at the mass, the percent mass of the elements, it's 27.29% carbon and 72.71% oxygen. Since oxygen is slightly greater in mass, the percent total of the mass is slightly higher than the 67% that you would expect from a 2/3 oxygen ratio. How do we figure out what the percent of the mass is? Well, the honest truth is it's pretty straightforward. What you're going to do is take the mass of the element and divide it by the total mass, and then multiply times 100, because that's what percent means. Percent per 100. So let's take this example where we've got masses given to us. We have a compound that contains only iron and chlorine. It just has those two elements in the substance. We take a sample that is both elements combined, and it weighs 2.56 grams. And then we decompose it, we break it down to its part, and the chlorine gets driven off because chlorine is a gas, and we're left with 0.88 grams of iron. The question would be, what is the percent composition of this substance? Well, the first thing you would do is figure out the percent iron. Well, the percent iron is 0.88 grams of iron divided by the grams total. And times 100, you find out you have 34% sig figs. 0.88, 2 sig figs, 34. Then what you're going to do to figure out the chlorine is take 2.56 grams, which is the total, subtract the iron. That will tell you how many grams was the chlorine, and then divide that by the total. So we find that the mass of the chlorine was 1.68 divided by 2.56 to sig figs, that's 65.6% chlorine. Now notice these two numbers do not add up to be exactly 100. And that's okay, because the way we obtained the percent chlorine was to a higher degree of precision than the way that we obtained the percent of iron, because iron's mass only had 2 digits past the decimal, but the calculated mass of chlorine had 3 total significant digits. If you try to take the shortcut and say, well, I know that there's only two elements in the compound, iron and chlorine, I know 34% of it is iron, and you just subtracted that from 100 and got 66. That would be equally correct, but the sig figs would be different. This is one of these situations where the method that you actually use to determine the percent composition might give you different amounts of significant digits. That's a little different. That's a little odd. Okay. Now, the other way that you could actually calculate the percent composition is if you were given the formula. So, for instance, if I had the formula of sodium phosphate Na3PO3, and I were to try to figure out the percent composition of that substance, one thing about all three of our pieces of today, the empirical formula, molecular formula, and percent composition, that is very, very critical to make this easy is that all three do not depend on the size of the sample. The percent of sample that is in a big sample, little sample, whatever, is going to be the same. So I need to determine what size sample I want to use for determining my percent composition from a formula. The easiest way to do that is to simply say, well, let's say I have 1 mole of this sample. And what that does to make life easier is if that's 1 mole of the sample, that's the size sample I use, well, I know I have 3 sodium, so I have 3 times the molar mass of sodium as my total mass that came from the sodiums. And I have 1 times the molar mass of phosphorus to give me the mass that came from phosphorus, and 3 times the molar mass of oxygen to tell me the mass that came from the oxygen. And then I know the total mass of the sample because I can add them up and do my sig figs to find out that I had 148.9413 grams. Now, that may not seem super simple and convenient because the numbers are so big, but this is the most precise way to do that. To assume you have a 1 mole sample, determine the molar mass of the sample, determine the masses that came from each one of the elements. You see where I'm going with this. And then you're going to, next, for each one of the elements, take the mass that came from the element, divided by the total, multiply times 100. There's my percent, 46.97777% sodium. For phosphorus, take my mass that came from phosphorus, divided by the total, times 100, 20.79595% phosphorus. And same with oxygen. Percent that came from the oxygen only, divided by the total times 100, you get a number. Now, one thing you need to note here is when you're getting to percent composition from a formula, since the tool that you're using to measure the masses is the periodic table, your precision for your masses is going to be very, very good. Okay, and these 3 numbers should add up to 100 or really close to it. Probably out to like the 4th or 5th digit might be off a little bit because of sig figs, but you're going to have these numbers should add up to be very close to 100 total grams. The next thing we're going to do is figure out what the empirical formula is of different substances. So the empirical formula, what is it? It is a simplest whole number ratio of elements. So what I mean there by simplest whole number ratio is pretend I have a compound that is C2H2. C2H2. That actually happens to be a compound of acetylene and is used in welding torches, but C2H2 is a compound. That compound's formula can be simplified down to C1H1, and that would be the empirical formula for acetylene, which has a molecular formula of C2H2. So you're looking at the simplified, how simple can I make the ratio of the elements? Well, the ratio of the elements is good, but what we're going to do is realize that since the number of atoms in a mole is the same, no matter what the atom is, that we're going to go ahead and determine a mole-to-mole ratio, and then that mole-to-mole ratio is going to be equal to our atom-to-atom ratio. Let's see this in action. So again, there's a couple different ways you can get information or data that can allow you to get the empirical formula. Probably the first way, the most common way, is to be given masses. So if I have masses, what you're going to do is convert each mass into moles. Each mass you're going to convert into moles by dividing by the atomic mass. That is very, very important. You're going to divide by the atomic mass. Even in those diatomic elements, you're not going to divide by the H2N2O2. You're going to be dividing by the atomic mass directly off the periodic table to get the moles of that element. Then you're going to figure out the simplest whole number ratio by dividing by the smallest of those number of moles. And then finally, make sure they're all whole numbers, and then you're good. You have an empirical formula. Let's try it. So ethanol is a compound that contains only carbon, hydrogen, and oxygen. This is a very common way to actually determine a empirical formula is you measure a mass. So the sample in the beginning is 8.57 grams, and then I break it down, decompose it, and I get that there's 4.47 grams of carbon and 2.98 grams of oxygen. How I get that is inconsequential here. I just know those are the masses of those two elements. Notice I've also not given you the mass of the hydrogen, but we can get that because we can subtract these two numbers, the carbon's number and the oxygen number, from the overall number to get the leftovers, since we said that it only contains 3 elements to get the hydrogen. So first step is divide by the atomic mass of each. So to take the mass of the carbon divided by the atomic mass of carbon, take the mass of the oxygen divided by the atomic mass of oxygen. And this should be an O here. I made a mistake. Sorry about that. And then take the hydrogen and figure out the hydrogen by subtracting the 2 and getting the number of moles of hydrogen. So step 1, convert each one of the masses into moles, dividing by the atomic mass. Step 2 is to divide by the smallest. So we're going to divide by the smallest. The smallest here is the 0.186. So if I divide each one of these numbers by 0.186, I get that carbon is 2, oxygen obviously is 1, and then 0.11 divided by 0.186 is really, really close to 6. Now, when I say really, really close to 6, you're going to have to get used to the fact that it's going to be slightly off, but yes, it is going to be very, very close to 6 if you do the math, which means my formula is C2O1H6. And more commonly, when you're talking about hydrocarbons, the carbon comes first, the hydrogen comes second, and all the other stuff comes later. So the correct formula for ethanol that you normally will see written down is C2H6O1 or O. Now, for the Google Classroom homeworks, it is very clear in there that you want to put the subscript 1s so that it can actually check your answer and tell you whether you're right or wrong. So please make sure you put that 1 on there, even though I didn't do it here for edification. This is what you would see for the empirical formula for ethanol if you were to look it up in the book. Okay, so another way to get empirical formula is to get it directly from percent composition. So the first step, there's 3 steps involved. The bottom 2 steps are exactly the same as we just did on the previous example, but the first step is the kicker. You're going to assume a 100-gram total sample. Now, why would we do that? Well, the main reason is that we know our percent of mass of the total sample, so it'll make math really, really easy if we choose a 100-gram sample. Well, if something was 25% carbon, 25% carbon, and we had a 2.73 gram sample, well, then I'd have to whip out my calculator to find out what 25% of 2.73 was. However, if I assume a 100-gram sample, then I can do that in my head. 25% of 100 is 25. So it makes the first step very, very easy. That's the only reason to choose a 100-gram sample. You can choose whatever gram mass you want. Actually, this process will work very, very well regardless. Then you're going to do just like we did in the previous example. Take those masses you have for each one of the elements and divide by the atomic mass, and then determine the empirical formula or the smallest ratio by dividing by the smallest. So let's see this in action. So I have a compound that is 28.8% magnesium, 14.2% carbon, and 56.9% oxygen. And I want to know what's the empirical formula. So the steps are, first off, assume a 100-gram sample. So if I assume a 100-gram sample, all those percentages become masses, and that's good. That's easy. Second step, divide each one of the masses by the atomic mass. So I'm going to divide the magnesium mass divided by the magnesium's atomic mass, take the carbon's mass divided by the carbon's atomic mass, and take the oxygen mass and divide it by the oxygen's atomic mass. Again, oxygen is not the O2 number, it is the oxygen number just for O. I get a ratio of these three numbers, and then the last thing we need to do is determine the ratio. And we do that by dividing by the smallest of the numbers. So if I have these three masses, and I want to take these three masses and divide by the smallest, which happens to be 1.18, then I'm going to get a 1 to 1 to 3 ratio, which means this compound is Mg1C1O3, more commonly written as MgCO3, which is magnesium carbonate. So empirical formula can be determined from either masses or from percent composition. Now, the last thing that is part of this video for this week is the idea of the molecular formula. And as I said earlier, the molecular formula is the true formula. So if acetylene is C2H2, that's the actual number of elements. There are 2 carbons attached to 2 hydrogens. Actual number, not ratio, not smallest, simplest number ratio. That is the empirical formula, but the actual number of each of the elements in the formula. There are 2 carbons and there are 2 hydrogens. So that's the one twist to a molecular formula. But the process is very, very, very similar as to how to determine the molecular formula. As a matter of fact, in order to determine a molecular formula, the first thing you're going to do is determine the empirical formula. So let's look at this example. So here's the twist. Almost all the time, or in order to determine the molecular formula, you're going to need one more piece of data. And that's this first thing that's given to you. The molecular mass or the molar mass of the original substance, the big substance. This one has a molar mass of 180.2 grams per mole. Then it gives you information very, very similar to what we had before. In this one, they're giving you percent composition. You could also get the masses of each one of a sample and an element, all the things. That's in order to get the empirical formula. You want to get the molecular formula of the compound. So the steps involved are, first and foremost, do exactly what we've done in order to figure out the empirical formula. Then we're going to find the molar mass of the empirical formula, compare it to the molar mass of the molecular formula, and then adjust your subscripts accordingly to figure out the subscripts on the real formula. So, first step, 40% carbon, 6.71% hydrogen, 53.28% oxygen. What's the empirical formula? So, real quick, take the masses, divide by the atomic masses, get a number of moles, divide through by the smallest, and get a ratio. The ratio is 1 carbon, 2 hydrogens, 1 oxygen. It's a 1 to 2 to 1 ratio. Second step, find the molar mass of the empirical formula. So if it's 1 carbon, 2 hydrogens, 1 oxygen, the molar mass when you do that is 30.0260 grams per mole. That's my molar mass of my empirical formula. Step 3, determine the ratio of the molar mass of the molecule to the molar mass of the empirical formula. Well, the molecule had a molar mass of 180.2. The compound had a molar mass of 30.0260. So if I divide those two, I get a number really, really close to 6, which means my compound is 6 times larger than my empirical formula. My molecule is 6 times larger than my empirical formula, which means I need to now multiply my subscripts of the empirical formula by the ratio. Since the empirical formula was 1 to 2 to 1, and my compound is 6 times larger, I'm going to multiply all my subscripts by 6, and I get C6H12O6, and that is the molecular formula for glucose, a very important compound that you'll just study in biology next year. So that's how you determine the molecular formula. It has that one extra step where you have to compare your empirical formula's molar mass to your molecular formula's molar mass, and then multiply accordingly. So hopefully that makes some sense. There's 3 aspects in this video that we went over. percent composition, empirical formula, and molecular formula. So what's next? That's the only video that we're going to do for this week. Next week, we're going to combine stoichiometry, the stuff that we did last week, and a little bit of what we did this week. And we're going to combine it with balanced chemical equations and talk about what happens during a reaction. What happens to the masses of the different substances during a chemical reaction? This is where we actually truly grab a hold of stoichiometry and how that connection takes place. So hopefully everybody is being healthy, safe, and practicing social distancing. I hope to see you guys real soon. This has been quite the challenge, this distance learning, and I appreciate all the support that I'm getting from everybody and trying to stay engaged with the classroom in its present form. If you like this video, get anything out of it, and it helps you with your homework associated with the content, please hit that like button. If you aren't already subscribed, please subscribe and hit that notification bell. I will see you on the next video, or I will also see you this week on Tuesday and Thursday in our Flex Hour on Microsoft Teams. Today is May the 4th, Star Wars Day. May the 4th be with you. I hope to see you guys real soon. Have a great day. Toodles.